Hello, my name is Charles King, and in this presentation I'm going to be critically evaluating the application of density-dependent groundwater flow models to simulate climate-driven seawater intrusion in coastal aquifers. Instead of merely reviewing model results, this analysis emphasizes modeling methodology, specifically examining how boundary conditions, climate forcing strategies, calibration approaches, and structural design choices affect predictive reliability under future climate change. So, coastal aquifers are increasingly vulnerable to three interacting pressures: sea level rise, climate-driven variability in recharge, and groundwater abstraction. Sea level rise and recharge variability are widely recognized in literature as dominant drivers of coastal aquifer salinization, and due to the impracticality of direct field experimentation and study, numerical modeling serves as the principal method for assessing future intrusion risk and informing management decisions. Accordingly, this review addresses the following question: how do modeling assumptions, particularly conceptual boundaries, recharge projections, and parameter estimation, influence predictions of seawater intrusion? Now, the objective is not to identify the most effective study, but rather to determine the primary sources of predictive uncertainty across various modeling frameworks. Seawater intrusion is fundamentally a density-dependent process. Freshwater has a density of approximately 1,000 kilograms per cubic meter, whereas seawater is approximately 1,025 kilograms per cubic meter. And this density contrast produces a wedge-shaped saline interface beneath the coastal aquifers, as depicted in the image on the screen. Importantly, groundwater flow and solute transport are coupled processes. Density depends on salinity, and salinity distribution depends on groundwater flow, and this feedback requires variable density modeling. Under hydraulic stress, such as reduced recharge or increased pumping, inland hydraulic gradients weaken and the saltwater wedge migrates landward. In all three case studies that we review during this presentation, they simulate this process using CWAT-based variable density modeling frameworks. Referring back to the diagram on the screen, denser saline water forms a wedge beneath the freshwater lens, and the interface migrates inland under hydraulic pressure. The three selected studies shown in this table on the screen represent contrasting coastal environments and modeling strategies. Rasmussen et al. 2013 models a drained island aquifer influenced by land reclamation and drainage canals. Safi et al. 2018 focuses on an urban coastal aquifer under significant abstraction pressure. Lyra et al. 2024 applies an integrated modeling system that couples surface hydrology and groundwater flow under ensemble climate projections. Although the hydrogeological settings differ, all three studies apply three-dimensional, transient, finite difference variable density modeling. This methodological consistency enables meaningful comparisons of modeling decisions rather than focusing on differences in numerical algorithms. Now, all three studies employ finite difference discretization and transient simulations, and variable density coupling is achieved using CWAT or equivalent mod flow-based frameworks. However, there are alternative density-dependent modeling frameworks available, and they have been applied to climate-driven seawater intrusion, for instance, in Chun et al., where they used Sutra. This highlights that differences in predicted intrusion are not primarily driven by solver choice, but rather by conceptual boundary design, climate forcing implementation, structural heterogeneity of representation, calibration, and parameter estimation methods. And these modeling dimensions provide the basis for a structured comparison for the three studies during this presentation. Now, to ensure a consistent and systematic evaluation, the three studies are compared across 5 key modeling criteria, and these criteria reflect the primary modeling decisions that influence density-dependent intrusion behavior. They include boundary condition implementation, climate forcing strategies, grid and hydrostratigraphic representation, and calibration and validation approaches, as well as sensitivity analysis. Now, each of these components directly affects how uncertainty propagates through the model and influences predictive reliability. And I will now examine each of those criteria in turn. Starting with boundary control and system sensitivity. Boundary implementation emerges as one of the most influential modelling contrasts. In Rasmussen, the aquifer is heavily influenced by artificial drainage canals, and those canals effectively impose hydraulic head controls inland, altering the natural balance between recharge and discharge. This system behaves as either head controlled or flux controlled depending on how the boundaries are conceptualized, and this significantly affects simulated wedge position and migration. In Safi, however, abstraction wells represent a major internal boundary stress. Although the coastline is treated as a specified head boundary, pumping modifies inland gradients, often exerting a stronger influence on intrusion than sea level rise alone. This demonstrates how internal stresses can dominate over external coastal forcing. Now, as shown in the model to the right on screen, the coastline is implemented as a specified head boundary, while abstraction wells act as internal stresses that modify the hydraulic gradients in the inland region. Lyra implements a transient coastal boundary condition, updating sea level rise annually under RCP 4.5 and RCP 8.5 scenarios. This dynamic boundary allows gradual adjustment of the saline interface over time, rather than imposing a static shift. Now, examples I've given illustrate that boundary conditions are not merely numerical settings, and they are conceptual decisions that determine how the model responds to stress. Small differences in boundary implementation could produce substantially different intrusion trajectories. Therefore, predictive outcomes are highly sensitive to how coastal and inland boundaries are defined and updated. Next, we're looking at climate forcing implementation. The sophistication of climate forcing increases across the three studies. Rasmussen applies fixed increments of sea level rise and recharge change, whereas Safi evaluates scenario-based combinations of population growth, abstraction, and sea level rise. Lyra, however, integrates 19 MedCordex regional climate models under RCP 4.5 and RCP 8.5, applying bias correction and transient forcing. While increasing climate complexity improves realism, it also amplifies recharge uncertainty. Recharge projections diverge significantly across climate models. Therefore, increasing the complexity of climate forcing does not eliminate uncertainty, rather it reveals and highlights it. Next, we're looking at the calibration and parameter confidence. Calibration approaches again differ across the three studies. Rasmussen calibrates the model to hydraulic head observations and compares simulated salinity distributions with independent geophysical data. Safi, however, applies PEST, with pilot points to estimate spatially distributed hydraulic conductivity fields, allowing parameter adjustment during calibration. Lyra, on the other hand, reports high Nash Sutcliffe efficiency values of 0.98 for groundwater flow and 0.92 for transport, indicating strong agreement between simulated and observed data. Now, if you don't know, the Nash Sutcliffe's efficiency is a statistical measure of model performance, and values close to 1 indicate a very good fit. However, high NSE values do not necessarily guarantee reliable salinity prediction. It's important to recognize that key transport parameters such as dispersivity and effective porosity are often poorly constrained in coastal systems. While hydraulic conductivity may be estimated through pilot point inversion or calibration adjustment, dispersivity is rarely measured directly at the basin scale. As a result, simulated mixing behaviors can be sensitive to assumed parameter values rather than uniquely determined by field observations. Therefore, even well-calibrated, density-dependent models retain parameter non-uniqueness and predictive uncertainty, particularly under future stress scenarios. Next, looking at resolution and structural detail. Structural complexity also differs across studies. Rasmussen uses a 50-meter grid with 32 vertical layers, subdividing chalk units to represent depth-dependent conductivity. This cross-section, shown at the bottom of the screen, illustrates the layered hydrostratigraphy used in Rasmussen's model, including the subdivision of chalk units to represent depth-dependent conductivity. Lyra applies a coarser 150-meter grid at the basin scale, and this higher spatial resolution enhances structural realism. However, it also increases parameter uncertainty and computational requirements. Notably, increasing model resolution does not necessarily reduce predictive uncertainty when parameters are poorly constrained. Looking ahead now at our synthesis of the three studies, starting with recharge as the dominant climate uncertainty. Now, across all three studies, recharge variability emerges as a dominant driver of intrusion response. Lyra's ensemble projections that demonstrate substantial divergence in recharge trends under different climate models. The ternary diagram to the left shows the relative contributions of recharge, abstraction, and seawater intrusion, highlighting how projected changes in recharge shift the system balance under different climate scenarios. Rasmussen, on the other hand, shows that recharge change can produce intrusion responses comparable to those from sea level rise. Recharge projections are inherently uncertain due to climate variability and downscaling assumptions. Accordingly, recharge uncertainty constitutes a primary driver of predictive variability in density-dependent coastal models. Next, we're looking at boundary conditions and how they shape the model's response. So, boundary assumptions obviously strongly influence model behavior. Drainage infrastructure in Rasmussen fundamentally alters hydraulic gradients. The conceptual evolution figure to the right illustrates how drainage and reclamation fundamentally altered boundary controls in Rasmussen's system during its study. And this reinforced the structural importance of conceptual boundary assumptions. Abstraction stress in Safi's study dominates intrusion dynamics. Transient coastal boundaries in Lyra's study shape long-term wedge migration. This goes to suggest that intrusion predictions are highly dependent on conceptual model framing, and boundary implementation is not a minor technical consideration. It instead exerts a significant structural influence. For our final synthesis, calibration does not eliminate uncertainty. Even well-calibrated models retain predictive uncertainty. Hydraulic conductivity distributions remain uncertain, particularly in heterogeneous coastal sediments, and salinity data are typically sparser than head data. And as a result, multiple plausible parameter fields can reproduce historical observations while diverging under stress scenarios. Overall, calibration enhances model credibility. However, it doesn't eliminate uncertainty in long-term projections. In conclusion, density-dependent groundwater models are indispensable tools for assessing climate-driven seawater intrusion. All three studies reviewed in this presentation project increased intrusion risk under future climate and abstraction stress. However, predictive reliability is constrained, primarily by recharge projection uncertainty, boundary condition assumptions, and parameter non-uniqueness. And these limitations are more significant than those imposed solely by numerical model complexity. My closing statement is that a comprehensive understanding and explicit evaluation of these modeling sensitivities are essential for robust coastal groundwater management. Thank you.